My name is Susie Shee. I am the curator of the July Lectures in Physics. For those of you who've been coming loyal fans for many years, you'll know that Professor David Jamison curated these lectures for almost 20 years. I'm pleased to say that, as usual, we have 4 lectures this year every Friday evening for the next 4 evenings, and David will be giving the last of those lectures, just so you're aware. So he will be making himself known to the audience again. But this evening, it is my great pleasure to have Professor Nicole Bell here with us tonight. Nicole is a theoretical physicist who works in particle astrophysics, and she leads the theory program in the ARC Centre of Excellence for Dark Matter Particle Physics. She's also the Vice President of the Australian Institute of Physics, and she's worked in the US at Fermilab, at Caltech and other places, and her research is award-winning in many different ways, from places like the Australian Academy of Science, from the Australian Institute of Physics and so forth. Now this evening Nicole is going to be speaking to us about the quantum foundations of the universe, the creation of matter, which is the first lecture, of 4 that we're going to be having in the July Lectures in Physics this year, all of which this year are themed around quantum mechanics basically, and also its impact all the way from our understanding of the universe to the next generation of computing, to chemistry, all the way, just all the ways it impacts our lives and may impact our lives in the future. Could you advance the slide by 1 for me? Thank you. So just before we begin this evening, I'd like to acknowledge first of all that it is NAIDOC week, and that we are presenting this lecture this evening on the lands of the Wurundjeri people of the Kulin Nation, who've been the custodians for many thousands of years, and pay our respects to their elders past and present, and acknowledge their presence as the first scientists of this land as well. Now, you've heard enough from me. The main star of the show this evening is Professor Nicole Bell, so without further ado, I'd like to ask you to give a warm round of applause and introduce Nicole. Thank you.
Thanks, Susie. Thanks, Susie. Okay, so I'm going to talk about the quantum foundations of the universe, and in particular, the creation of matter. And so the basic premise of this talk is that we actually need quantum mechanics to understand the universe. Usually when somebody says quantum mechanics, you think of little things, right? Atoms, something smaller than an atom. But I'm going to talk about the universe, which is, the biggest scales we can talk about. And so here is a picture of the evolution of the universe, right from creation at the Big Bang through to the present day, so from the beginning of the universe all the way through to the end. And I'm actually going to focus on the first 3 minutes. I'm a particle physicist. All the interesting particle physics happens in the first 3 minutes. And in fact, and the rest is astronomy. And what happens in the first 3 minutes sets the scene for everything that happens later. It's all laid down right at the beginning. And quantum mechanics is absolutely a foundational part of what goes on. Okay, so here's a quick summary of what I'm going to talk about. I'm going to tell you about dark energy. I'm going to tell you about the origin of structure, that is, the galaxies and clusters of galaxies in the universe. And when you think about galaxies and clusters of galaxies, quantum mechanics doesn't spring to mind, but actually it's all quantum. Generation of producing matter, and why there's matter in the universe at all. Why is there something instead of nothing? It's entirely to do with quantum mechanics. And so we'll see as we go how this comes about. So fundamentally, we can ask, what is the universe made of? And broadly speaking, we can break it up into 3 significant pieces, one of which is the dark energy. In fact, most of the energy density in the universe is this dark energy, which I'll talk about in a little bit. There's a lot of dark matter in the universe, and then there's a small amount of ordinary matter, the stuff that's labelled atoms. This is the stuff that we know and love and know a lot about. Actually, that's a small fraction of the universe. But in fact, all 3 slices of this pie need quantum mechanics to be properly understood. All right, so I'm going to give you Quantum Mechanics 101 in about 3 or 4 slides, and then we're going to use the concepts from here later on. So fundamentally, quantum mechanics is about the fact that everything is both a particle and a wave. In classical physics, we're used to thinking about particles like electrons or atoms or balls as being particles, and other sorts of things like light waves or sound waves or radio waves or waves of water as being waves. In quantum mechanical description of the world, everything is both a particle and a wave, and it's this so-called wave-particle duality which is at the heart of quantum mechanics, and explains many of the things that, many of the weird quantum phenomena that we're going to talk about. Another feature that's inherent to quantum mechanics is that it's probabilistic. In classical physics, we talk about things like trajectories of particles. On the plot, on the diagram on the left, I have a classical picture of the atom in which I have electrons whizzing around the atom on orbits, sort of well-defined trajectories. The quantum mechanical picture of the atom is quite different. The quantum mechanical picture, the electrons live in those fuzzy blobs, and we can't talk about the trajectory of the electron. We can just calculate probabilities for the electron to be in certain locations. We can't tell you exactly where it is. We can just calculate the probability of it being here or there. And quantum mechanics is fundamentally probabilistic, and we're going to see the implications of this as we go. Another fundamental feature of quantum mechanics is quantum superposition. And put simply, that's the idea that a particle can be in a so-called superposition where it can behave as though it's both here and there at the same time. And we can calculate the probability it's one spot or the other, but it's actually in both places. And so there's famous thought experiments you can do with quantum superpositions, and then the most famous one that you may have heard of is something called Schrodinger's cat. So Schrodinger was one of the pioneers of quantum mechanics and did a thought experiment in which he had a cat in a box, and the cat was in both the state of being dead and the state of being alive at the same time, until someone opened the box and took a measurement and found out with certainty, the state of the cat. So in quantum mechanics, we find superpositions of systems in different physical states, and we're going to see what that does for our universe. Another thing you might have heard about with quantum mechanics is that there's uncertainty. So this is the famous Heisenberg uncertainty principle, which says that if you take the uncertainty in location, position, and you multiply it by the uncertainty in momentum, that has to be larger than or equal to some number. And this is not anything to do with our inability to make precise measurements. This is a fundamental uncertainty. No matter how precisely you measure something, there is some fundamental uncertainty that you can't reduce. And so one way of interpreting what this equation says is that the more accurately you know position, so the smaller you make the uncertainty in position, the less accurately you know the momentum, that is how fast the particle is going. But quantum uncertainty is you'll see, is going to play a significant role in the evolution of the universe. Okay, so this is... And it's not just position and momentum, that is, location and how fast something is going. There's pairs of things that have this same sort of uncertainty relation. And the one that's going to be most important for us is this uncertainty relation that connects energy and time. So there's some uncertainty in the energy delta T multiplied by some uncertainty in the amount of time the system spends in that state, which has to be bigger than this quantity, which is h power 2, which is a teeny tiny number, but it's not zero. So we have uncertainty in energy over short periods of time. And now I'm going to jump to the universe. So what I have on the left is a picture of, well, both pictures are a picture of the vacuum. So the vacuum you should think of as being empty space. But in fact, empty space is not empty. And this matters for the evolution of the universe. It matters quite a lot. So in quantum mechanics, because I have this uncertainty in energy, I can create virtual particles. So on the left, I have virtual particles. I have a particle and an antiparticle, which can pop into existence for a short amount of time, which satisfies this uncertainty relation. Uncertainty in energy times uncertainty in time is bigger than, is about equal to Planck's constant h bar. And so empty space is not empty because I have these quantum virtual particles popping in and out of existence all the time. And so this movie on the right that was produced by a colleague in Adelaide, actually, is a simulation of the quantum nature of the vacuum. It's these virtual particles that have some energy for very short periods of time that, you know, relies upon this quantum uncertainty relation that's in the vacuum. So empty space is not empty. The vacuum's got quantum fluctuations in it. And these quantum fluctuations have important implications for how the universe behaves. In fact, they have two important implications for how the universe behaves. So again, these are the same virtual particles on the previous slide, little bits of energy, and we can calculate the energy of empty space. Empty space is not empty. Empty space has got energy, and we can calculate how much energy the empty space should have. And what this corresponds to in the pie chart over here is this. It's dark energy. Dark energy is the energy of empty space. And what dark energy does for the universe is that it takes our universe, which we know has been expanding ever since the Big Bang, and speeds up that expansion, accelerates it. So this dark energy is actually really important for the way the universe evolves. And what is it? It's the energy of empty space. And why is there energy in empty space? Well, it's because the vacuum has these quantum fluctuations. Unfortunately, if a theoretical physicist tries to calculate how big the energy of empty space is, we get the wrong answer. We get the wrong answer by really quite a lot, a huge number. This has been called the worst prediction of theoretical physics. So the vacuum's got energy, it's these quantum fluctuations, but there's something we don't understand about how to calculate it. Nonetheless, the vacuum does have this energy. This is the dark energy whose size has been calculated quite precisely because we know how fast the universe is expanding and we know how fast that expansion is speeding up. Okay, but in addition to being the dark energy, the fact that empty space is not empty also fundamentally leads to structure in the universe. So on the left, again, this is the same as the movie from before. These are the quantum fluctuations in the vacuum. And in fact, those quantum fluctuations in the vacuum eventually led to this on the right, which is a simulation of galaxies in the universe. So on the right, in the blue, we have the spots that are sort of brighter than the other spots are regions where the density in the universe is higher, that is, there's more galaxies and clusters of galaxies, and the dark spots amongst the blue are the voids in the universe where there's less matter, where there aren't stars and galaxies that glow. This is a simulation, but it matches very closely with the structure that we see in the universe. And where did the structure come from? Well, this structure was seeded by quantum fluctuations in the early universe. And to understand that a little bit more, I need to talk about something called cosmological inflation. Okay, so again, this pink picture is a simulation of the structure in the universe. So the pink on this slide is the same as the blue on the other slide. It's a simulation of the galaxies in the universe today. And you'll see that there's sort of regions that are brighter than others. Those are dense spots. And you'll see that there's regions that are darker than others. Those are spots that are less dense, spaces between clusters of galaxies. And you'll see it has this sort of filamentary structure, like this spider web. This very closely matches what astronomers see when they look at the structure on the larger scales in the universe. But maybe the most striking feature of this picture is it's more or less the same everywhere, right? There are little spots that are brighter and darker than others, but on a global picture, you know, it's like it's uniform. You could tile this across the room. It's the same everywhere. It's featureless. And so the universe looks the same everywhere. It's very homogeneous, it's uniform. It looks the same in all directions. In terms of the curvature of the universe, of the space-time, the universe is also very flat. It's in some sense featureless. And you can ask the question, why is the universe the same everywhere? And in fact, you know, this is an important question, and it's an important question because earlier on in the history of the universe, the bits of the universe that could talk to each other were smaller. So if the whole rectangle is the observable universe today, in the past the observable universe was smaller, say this circle here, wrong button, that circle here, and this part of the universe and that part of the universe, if we go back early enough, were not in contact with each other. That is, that they were so far apart that you couldn't send a signal from this spot to that spot within the lifetime of the universe. The universe wasn't old enough for light even to travel from here to there. And so if I have these spots in the universe, this one over here and that one over there, that are too far apart to be in communication at all, then it seems very odd that the universe should look exactly the same here as it does there, if there's no way to send a signal backwards and forwards between the two. They should be quite different. Any process that will sort of wash things out and make them look the same everywhere hasn't had time to function yet. And so this is one of the motivations for invoking something called cosmic inflation. So we know the universe is expanding, and cosmic inflation proposes that not only is the universe expanding, but that in the first sort of moments of the universe, not only was it expanding, but the expanding was extra fast. So if this red line is the standard sort of expansion of the universe, cosmic inflation says that there was a brief moment right at the beginning where the expansion was even faster and blew the universe up really big, really quickly. So what inflation did was to take a tiny patch of the universe before inflation and blow it up really, really big. And the implication of that is that then if I talk about the observable universe today, so the yellow region in this diagram, then everywhere in the observable universe today was inside the little patch right at the beginning that was small enough that it could be the same everywhere because light signals could be sent backwards and forwards across that teeny tiny patch. So this cosmic inflation explains why two patches of the universe that early on in time didn't look like they would have any way of communicating with each other actually were in causal contact. Explains why the universe looks uniform on scales bigger than we might expect it to. Okay, so inflation does this, but inflation also blows up the quantum fluctuations at the beginning of the universe. All right, so inflation made the universe look very, very uniform. Blew it up really big, made it really flat, made it look the same everywhere. But not completely uniform, because remember, we have this vacuum, and this vacuum's got fluctuations in it, teeny tiny quantum fluctuations. Inflation blew those teeny tiny quantum fluctuations up, and those fluctuations actually eventually became the seeds of structure. So at the beginning, here, quantum fluctuations got blown up in inflation and eventually became the structures that we see in the universe. So what I've got the coloured blobs on the right is actually an image of the cosmic microwave background. This is just light that's left over from the Big Bang. The fluctuations you see in the cosmic microwave background you can think of as being the primordial fluctuations that were there right from the beginning that got blown up by inflation. They actually get stretched to superhorizon scales, in fact, and then they evolve after they come back into the horizon later, but that's not so important. But originally, why are there some spots that are the red spots and the blue spots in this picture are regions of the universe that are a little bit more dense or a little bit less dense than others. Why is this fluctuation in the density? It's because of those quantum fluctuations. So a little bit of a closer look at that map of the fluctuations. So if we measure the temperature in the universe, it's the same everywhere. So we measure the temperature by measuring the light that was left over from the Big Bang. And that light has a temperature associated with it. That light is actually in the microwave energy range, which corresponds to a temperature of about 3 degrees. And it doesn't matter which direction in the universe you look, you measure the temperature of that radiation, that light, and you find it's about 3 degrees. In fact, it's not quite 3 degrees. There are some more decimal places that I haven't written down, but at this level it's 3 degrees everywhere. If I subtract off the 3 degrees, you see at the 3rd decimal place there's a slight variation. The red spot and the blue spot are regions that are a bit hotter and a bit colder than the average. This particular pattern comes about because the Earth and indeed our whole solar system is ploughing through this background radiation. But if I subtract that off as well, that's when I get this. And these are the leftover fluctuations after you subtract off the 3 degrees and you subtract off the motion of the Earth, and then you see in the 4th decimal place you see tiny variations where the temperature is a little bit hotter than 2.72 degrees and a little bit colder than 2.7 degrees, corresponding to regions of the universe that are a little bit more dense and a little bit less dense than the average density. And where did these fluctuations come from originally? Well, it was those quantum fluctuations that got blown up during inflation. So originally we had quantum fluctuations, and the amplitude of those fluctuations we can tell from that cosmic microwave background to be at about 10 to the minus 5 level. So this is this number at the top, the 0.00001. The cosmic microwave background is a snapshot of the way those fluctuations have evolved, and that's a snapshot of what conditions were like when the universe was 300,000 years old, so quite some time later. And then the regions that were a little bit more dense than others, eventually, under gravity, further condensed, and over time you get the evolution from the left over here, where things still look pretty uniform, but you can see there are fluctuations. And as time goes on and matter clusters under gravity, we end up with a universe like the one that we see today. And this is the one that matches what astronomers see. But the fact that you have structure in the universe at all and not just uniform density everywhere, you can trace to the fact that there were these primordial fluctuations, quantum fluctuations, right back at the beginning. Okay, so we have seen that. Am I doing for time? That's okay. We have seen that quantum physics, in particular those quantum fluctuations right in the first few moments of the universe, are responsible for the growth of structure. We've seen that the quantum vacuum means that the vacuum isn't empty. The vacuum has structure and the vacuum's got energy, and this is the dark energy we want. We're going to see that the quantum physics is also responsible not only for where the matter in the universe is, but also how much matter there is in the universe and what sort of matter we have in the universe. So I want to spend some time now talking about how matter is created in the universe, and another way of expressing that is, why does the universe have matter but no antimatter? And then I'm going to talk a little bit about dark matter. All right, so again, I'm talking about the first moments of the universe. So we've talked about the seeding of structure, but in fact, everything that happens sort of from the yellow through to the pink, it's all particle physics and nuclear physics, and it's inherently quantum mechanical. I mean, in order to describe what goes on there, we need something called quantum field theory to calculate it. It's all quantum, but there are some particular things that we can talk about where the quantum mechanics is really clear. Okay, so I'm going to talk about the creation of matter. Matter is made out of these fundamental particles, but the matter I'm going to talk about in terms of the ordinary matter of the universe is protons and neutrons. And protons and neutrons are made from these guys, the up and down quarks. We also have electrons in atoms, and the Higgs boson is actually going to play a starring role in this story. Okay, so how much matter does the universe contain, and why is it all matter and no antimatter? And in particular, why didn't the universe have matter and antimatter, and why didn't it all just annihilate with each other and go away and leave us with nothing? So why is there something as opposed to nothing? So first of all, what is antimatter? So antimatter is the idea that each particle has a partner. So take a particle that you've heard of, say the electron. The antiparticle for the electron is something called the positron, and it's very similar to the electron. It has the same mass, it has all the same properties, but the difference is that its electric charge is flipped. So while an electron has a negative electric charge, a positron has a positive electric charge. And this is the feature of all the antiparticles. They have the same mass, but they have the opposite charge. So in addition to electrons and positrons, I can have a proton and an antiproton, I can have a quark and an antiquark, there's a neutrino and an antineutrino. The particles of matter come in these particle-antiparticle pairs. In fact, it could be the case that the neutrino is its own antiparticle, but that's another story. And in fact, the existence of these antiparticles you can also think about in terms of quantum mechanics. In fact, antimatter was a prediction of relativistic quantum mechanics. When people first formulated quantum mechanics, we looked at a non-relativistic version of quantum mechanics. But as soon as you start to put quantum mechanics and special relativity together, and you can do this either in terms of something that we call relativistic quantum mechanics, or you do something similar in a formulation that we call quantum field theory, either way, you necessarily have antiparticles in the description. Okay, so nature has antiparticles. We've produced antiparticles in particle colliders. We see antiparticles in cosmic rays. But there's very little antimatter in the universe. Why is that? You might imagine that the universe had equal amounts of matter and antimatter, but we know that can't be the case. If we're matter, clearly. If there was a big patch of antimatter somewhere else in the universe, we know that can't be the case, because at the boundary between the matter region and the antimatter region somewhere else, matter and antimatter would be annihilating, producing an abundance of gamma rays, right, that astronomers will see. We don't see that. We see no evidence for separation of matter and antimatter in the universe. We conclude that actually there's very, very little antimatter in the universe. The amount of regular matter in the universe we've measured quite precisely. So this is the cosmic microwave background that I've already talked about. But in fact, this cosmic microwave background is useful to us for all sorts of reasons. We use it to make really precision measurements of cosmological parameters. And one of those measurements is how much ordinary matter is there in the universe. So we can tell from the amplitude of the hot spots and the dark spots how much matter there is in the universe quite precisely. We can measure how much matter, ordinary matter there is in the universe in another way. The universe at early times had sort of just protons and electrons, and at some point nucleosynthesis occurred, which produced the light elements, helium, deuterium, lithium, and so forth. And by calculating how much of the different light elements were produced, we can also figure out how much ordinary matter there was in the universe, and we get the same answer that we got from the CMB, which is good. And it's this number here. For every photon in the universe, we have 10 to the minus 10 baryons. So a baryon is a proton or a neutron. So that is for each proton or neutron in the universe, we have 10 to the power of 10 more photons. So this number is very small, but the point is that it's non-zero, and we know it's non-zero because we're here today made out of protons and neutrons. All right, so if the early universe had equal amounts of matter and antimatter, which kind of seems like the sensible state for the universe to be in, there'd be nothing left today. Long, long ago, all the matter would have found all the antimatter and annihilated with us and left nothing. Nothing actually isn't zero, nothing is this even tinier number, 10 to the minus 18, but for our purposes, that's zero. in fact, we've got a lot more matter in the universe than this. We've got a much bigger number. And so it must have been the case that long ago all the particles and antiparticles annihilated, but you had some leftover particles. And those leftover particles are the ones that are still present in the universe today. So in other words, in the first moments of the universe, for every 10 billion antimatter particles, there must have been 10 billion and 1 matter particles, and it's that one that didn't have anything else to annihilate with that's still around. So we need to figure out how to create a teeny tiny asymmetry between matter and antimatter in the early universe. And it really has to be in the early universe, because that's when all the annihilation that would have removed everything would have happened. All right, so why was there a tiny little bit more matter than antimatter in the universe? So one answer is, well, that's just the way it is, right? That doesn't seem like a good explanation. Physicists like symmetries, and this is not symmetric. But in fact, there's a better argument, and that is that this cosmic inflation, which blew the universe up really big and made it really uniform, also should have erased any pre-existing asymmetries and reset the universe in a really asymmetric state with equal amounts of matter and antimatter. So we need a mechanism to dynamically generate this asymmetry between particles and antiparticles. And to do this, we need quantum mechanics. We need lots of quantum mechanics. All right, so how do you create an asymmetry between matter and antimatter? The recipe is famous, but the way you cook this recipe is a matter of current research. So there are some requirements that you actually absolutely have to fulfill, but the way in which you fulfill them is something that we don't know yet, although we have ideas. So I'm going to tell you about some of those ideas. I'll come back to what these things are. In some sense, the easiest way to create an asymmetry between matter and antimatter is to do it in the decays of heavy particles. So this is an example that involves something called a heavy neutrino. It doesn't have to be a heavy neutrino, it's just a decay of a heavy particle. So on the left, I've got a heavy particle decaying into matter. And this same heavy particle, it turns out, can also decay into antimatter. So this particle that I've called N, which is actually a heavy version of the neutrinos that you might have heard of. Neutrinos are produced in nuclear fusion reactions that power the sun, for instance. The neutrinos are a particle that exists in nature. This heavy guy is a hypothetical heavy neutrino that's actually quite well motivated. But the point is that they can decay into particles, and they can decay into antiparticles. And then the question is, okay, is the decay into particles and antiparticles happening at the same rate, or could they be slightly different? And it turns out that they can be slightly different. But in order for them to be slightly different, we need something called quantum interference. So if you calculate the rate at which these heavy neutrinos decay into particles or antiparticles, without quantum corrections, they're identical, exactly the same. But quantum corrections changes that. So there's sort of two quantum things going on in this picture below. So what I've got here is, this is my original decay process. This heavy guy N is decaying into H. H is a Higgs boson, and L is, L can be an electron, say. So this is the same thing down here. This guy is a quantum correction. And what's in that circle blob in the middle are virtual particles. This is a higher order correction, a quantum correction involving quantum virtual particles that you need to add to get a more accurate expression for the rate at which these particles decay. And not only do we need virtual quantum particles in that loop, which is that blob in the middle, we also need quantum interference. So the quantum interference between these two contributions is actually what does it for us. And when you combine those things, you add this higher order term that's got the quantum virtual particles in it that gives you quantum interference. what that does then is give you that the rate at which these heavy guys decay into particles is no longer the same at which the rate at which these heavy guys decay into antiparticles. They're very slightly different, and that's enough to create this very small asymmetry between the amount of, say, electrons and positrons produced from these decay processes. This would happen in the first fraction of a second in the early universe. This particular process would create more electrons than positrons. Actually, we also need to have more protons than antiprotons, but there's a way to take asymmetries in electrons and turn them into asymmetries in protons and neutrons. And again, it involves quantum mechanics. So I have to talk about something called baryon number. So let me tell you what baryon number is. Baryon number is a symmetry. You should think of it like a charge. Okay, maybe the easiest way to say it is that I'm going to say that a proton and a neutron have got a baryon number of 1, and that the antiparticles have got a baryon number of -1. And this baryon number is a conserved quantity, just like electric charge is a conserved quantity, baryon number is a conserved quantity too. So we don't know of any physical processes that violate conservation of electric charge, and classically in the universe today, there are no processes that violate baryon number. So here's an example of a particle physics process. This, for example, this is a neutron decay. On the left-hand side of this reaction, I've got a neutron with baryon number equal to 1, and on the right-hand side, so neutron, and on the right-hand side I've got a proton that also has baryon number equal to 1. So on both sides of the process, baryon number is equal to 1. It's the same at the beginning and at the end, hasn't changed, hasn't been violated. And any reaction you can write down, any physical process, you look at the baryon number of the initial state and the baryon number of the final state, and they're the same. And this baryon number is a conserved quantity. But if we want to have physical processes that create asymmetries between matter and antimatter, there must be some processes for which that statement's not true. There must be some processes for which the baryon number of the initial state and the baryon number of the final state are different because we've converted matter to antimatter or vice versa. So this symmetry, which looks like it's a perfectly conserved symmetry at all times, actually has to be broken if we're going to create an asymmetry between matter and antimatter. And it turns out that the symmetry is broken. It's broken by quantum effects. So for a long time, it looks like this symmetry is a perfect symmetry. It turns out that this symmetry is called something, we call it anomalous. This is an anomalous symmetry. And that's a bit of jargon, but what that jargon means is that this is a symmetry that's an exact symmetry at the classical level, but once we quantize the theory, we write down a quantum version, that symmetry is broken. And that's kind of unusual. Usually when we have a classical symmetry like conservation of electric charge, take classical electrodynamics and then we quantize it to make quantum electrodynamics, electric charge is still an exactly conserved symmetry. Usually we take our classical theory, we write down the quantum equivalent, and the thing that were conserved in the classical theory are still conserved in the quantum theory. But sometimes that's not the case. We call these theories anomalous, and this is one of them. So baryon symmetry is actually violated at the quantum level. So this strange-looking beast on the left is a so-called spherulon, and this is a configuration of the quantum gauge fields which violates baryon number. And so I'm not going to get into the details of how it works, but you know, it's a quantum process that violates this classical symmetry, and it's this violation of this symmetry that allows us to create an excess of matter over antimatter when there was none there originally. Another way of thinking about this violation of the symmetry is actually making a transition from the bottom of some energy well to the bottom of an adjacent one, and there's a whole series of them, but actually going over these bumps changes the baryon number by integer units, actually by by 3 units. And in the universe today, this just doesn't happen. That's why we think baryon number is a good symmetry. 99% of the time, I'm assuming baryon number is a good symmetry. And that's because there's an energy cost to getting from the bottom of one well to the bottom of the next one. There's this huge hill, huge energy barrier that prevents me from going from that point labelled 0 to that point labelled 1. To get from 0 to 1, I need to climb this huge energy barrier, and that energy barrier is so high that in today's universe that doesn't happen. However, in the early universe, when the universe was small and dense and the temperatures were really high and all the particles were really energetic, because the particles were more energetic, they had enough energy to hop over that barrier, with ease. And so, in fact, baryon number violating processes were happening rapidly in the early universe. When do they turn off? They turn off at something called the electroweak phase transition, and that's a story that involves the Higgs boson. All right, so I'm going to tell you a little bit about the Higgs boson just to understand how this violation of baryon number comes about. All right, so this is a chart of all the fundamental particles in nature. Well, almost all of them. Dark matter's not there, but all the particles that we know about. And it's this guy, the Higgs boson, I want to talk about. So what is this Higgs field? The Higgs field, actually, it's the decade anniversary of the Higgs's discovery was last week, I believe. So we've known for sure that the Higgs particle exists in nature for 10 years now. And the Higgs has a special role out of all of these fundamental particles because it does two things for us. It breaks something called the electroweak symmetry, and it also gives mass to everything else on this chart. So it gives mass to all the fundamental particles. All right, so how does that symmetry get broken and how does the mass get generated? Basically, the universe starts out in a symmetric state, and this is the Higgs potential where originally we sit here, but we end up sitting down there, and when we roll down into this state, the symmetry is broken. And I'm glossing over some details because I want to get to the bits that matter for our discussion of the matter-antimatter asymmetry. So originally, this potential well in which the Higgs field, for the Higgs field, looks like this. Everything's symmetric. It's just it's all symmetric. But later on in the universe, when things cool down, it goes from the picture at the top to the picture at the bottom. And at that point, it's energetically unfavourable for the system to sit up here. It would really like to sit in the low energy state down here. And so we fall into this configuration. And at that point, we say that the symmetry is broken, the particles pick up mass, it does all the things that we know the Higgs boson to do. But how we get from this state to that state, the details of that are what matters. So, in fact, if the blue curve on the left represents the shape of this Higgs potential at the beginning of the universe when the temperature was really hot, what happens is that the shape of that potential changes as the universe cools down. And the shape of this potential is something that you can calculate. In fact, you have to calculate quantum corrections and high temperature corrections to get the shape of this thing right. So it's all quantum. Okay. And so as the universe cools, you go from the blue to the red to the black. And in fact, it could be the case that in order to make a transition from over here to over there, where it's energetically more favourable to live, it could be a situation that looks something like the plot on the right. You start off over here, and you end up down here. And then the question is, well, how do you get from this point to that point? I mean, if it looks like this, there's this energy barrier, this bump in the middle. Now, in classical physics, that energy barrier in the middle represents some hill you would have to climb to get over to end up down the bottom here in the true vacuum state. Quantum mechanically, though, you can tunnel through the hill. So this is quantum tunneling. My system starts off over here. Can I get over here? Well, classically, I have to climb the hill to get over here. I've got to have enough energy to climb the hill. But quantum mechanically, there is some probability that you can actually tunnel through the hill. The probability is low, and the probability becomes lower and lower the higher and higher that hill gets, or the higher and higher the energy potential barrier is that's stopping you from getting there, but the probability is non-zero. And so this quantum tunneling process can actually be relevant for the creation of the matter-antimatter asymmetry in the universe. So what happens then in this picture is that the Higgs field undergoes this phase transition whereby it tunnels from here to there by doing one of these quantum tunneling processes where you go through the hill. And in terms of what's going on in the universe, if I imagine that all the universe is sitting up here in this state that I've called the false vacuum, the entire universe is like that. That's represented by the blue background colour in this plot. And then in patches of the universe, we make a transition by tunnelling through the hill into this true vacuum. And in terms of this picture, what happens is a little bubble of true vacuum sort of is generated. As we tunnel through over here or over there, little vacuums of true vacuum True vacuums are generated in this sea of false vacuum. Eventually, everything tunnels through, and then we have true vacuum all over the universe. But as this phase transition is happening, we have this sort of bubble sort of structure to the universe where there's spots of true vacuum, little bubbles in a sea of false vacuum, and it's in these bubbles where the matter-antimatter asymmetry is created. So there's something called electroweak baryogenesis, and it's creation of the matter-antimatter asymmetry on the walls of these bubbles, in fact. So remember I said that there were these spherulon configurations which violated baryon number at the quantum level, and they were rapid in the early universe, and baryon number was being violated quickly, and in today's universe, it was energetically unfavourable for that to happen. That's completely switched off. In this bubble picture, violation of baryon number is fast in the dark blue region and is turned off when you're in the bubble of true vacuum. And so in the dark blue region and on the walls of the bubbles, that's where you can create the matter-antimatter asymmetry. And in fact, it's the walls of the bubbles where you really need it to happen because some of the other conditions that you need the universe to be in a non-equilibrium state to get something rather than nothing as well, are actually fulfilled in the walls of the bubbles. So you've got these bubbles that come about when you tunnel from the false vacuum to the true vacuum, and then in the walls of these bubbles you generate the asymmetry because baryon number is violated by this quantum anomaly process. In order for this to happen, you do need this tunnelling from the false vacuum to the true vacuum, this quantum tunnelling, and that all depends upon whether the shape of this Higgs potential is the right shape to get this phase transition. In the standard model of particle physics, it turns out that the Higgs potential doesn't have quite the right shape, but in fact we're only starting to test the Higgs sector of the theory, and so there's actually lots of space for the Higgs sector to be sufficiently complicated that this is actually why there's matter rather than antimatter. Why there's matter asymmetry in the universe. Okay, so before I leave the Higgs field, there's another interesting question you can ask, and you can ask, actually, is the universe in a false vacuum? So this was our Higgs field again, but it could be the case that even today, we're sitting in a configuration where we're here, but the universe has actually got the true vacuum would be over here. And if that's the case, then eventually we should tunnel from where we are today into the true vacuum state of the universe. The true vacuum is the lowest energy state. And whether or not there is some other vacuum that we're going to make a transition into at some point, is an open question. We haven't measured all the parameters associated with the coupling of the Higgs boson precisely enough yet to know whether that's the case, but we do know that we are very, very close to being in this metastable state. So that's quite interesting. The vacuum state that the universe is in is not necessarily a stable vacuum state. It could be metastable, and if that's true, then there's some teeny tiny probability that we would actually tunnel from where we are today into this state over here. How do we know? We need to figure this out. We need to calculate quantum corrections to the shape of the Higgs potential. Quantum corrections that involve how strongly the Higgs field couples to the top quark, in fact. Susie's going to cut me off in a minute. So I'm going to skim through that, I think. What time is it? Okay. So I was going to tell you about Big Bang nucleosynthesis, but I think I will skip that. And I wanted to finish by telling you a little bit about the dark matter. So I've spoken about, well, we just heard a lot about the Higgs, and it's the up and down quarks that make up the protons and neutrons that are the matter in the universe, together with the electrons that go into the atoms. But in fact, you know, in terms of what's in the universe, a big chunk of it is dark energy, the energy of empty space. There's the regular matter made out of things on this chart, and then there's the dark matter. All right, there it is. It's the dark matter. So what is that dark matter, and did quantum mechanics have anything to do with that? So we've got lots of evidence that that big chunk of the universe is in fact made of something dark. We know by looking at the universe on the scale of galaxies, or on bigger scales, the scale of clusters of galaxies, or even bigger scales of the universe as a whole. In order to reconcile observations, in order to reconcile our calculations with observations, we need dark matter in the universe, or we need quite a lot of it. And how much we need in order to make sense of the universe on all of these different scales is the same answer. We have a consistent picture of the universe, provided it's got a certain amount of dark matter in it. And we don't know what that dark matter is. We have some ideas. The most well-studied and well-motivated of those ideas is something called a WIMP. This means a weakly interacting massive particle. And the characteristic feature of these WIMPs is that early in the universe, they were in thermal equilibrium with everything else. So today, you know, we call it dark matter because we don't see it. It doesn't interact with light. It doesn't interact very strongly with any sort of ordinary matter, which makes it so hard to detect. But early in the universe, when the temperatures and the energies were high enough, actually the dark matter and the regular matter were interacting, and they were interacting rapidly, and the two sectors were actually in equilibrium with each other. And so there are some processes then that keep the dark matter talking to the regular matter. So this is dark matter annihilating into regular matter, or vice versa. These processes we imagine were rapid in the early universe, and the strength of those processes tells us something about how much dark matter there is in the universe today. A lot of my work and the work of my colleagues goes into what's in this orange blob in the middle. All right, so we believe that dark matter interacts with regular matter. We want to know how it interacts. How does the dark matter connect with the regular matter? What mediates the interactions? What's the form of the interaction? And so a lot of our thinking goes into, you know, the orange blob is a cartoon which parameterizes our ignorance, but what goes in there? So what goes in there are virtual particles. We just don't know what sort of virtual particle. There's something that we talk about called a dark photon. It could be any number of things, but they're quantum virtual particles. We want to know what virtual particles go in there and how they couple to the dark matter and to the regular matter. We have ways of going to look for We have ways of trying to understand how the dark matter couples to the regular matter. All right, and the tools at our disposal are that we can try and produce dark matter in particle physics colliders on Earth. we can try and look for signals of dark matter annihilation in the galaxy, or we can look for signals of dark matter bumping into ordinary matter and scattering in detectors on Earth. And research on all of these things is going on in the School of Physics here in Melbourne, and we've even got an experiment nearby in the Grampians, in fact, looking, this is an underground lab which is actually nearing completion in an old gold mine in the Grampians, and this is one of the detectors that will go down that mine in that laboratory in the mine once it's completed that will look for the scattering of dark matter. But fundamentally, why are we doing this? We're trying to understand what's in this orange blob. What's in that orange blob that gives the details of how the dark matter talks to the regular matter. And what goes in there are quantum virtual particles, and we use quantum field theory to calculate in detail how the dark matter interacts with the regular matter. So I think at that point I'm going to stop. And so really, quantum mechanics is responsible both for the creation of matter in the universe, and in terms of the matter-antimatter asymmetry, the creation of dark matter, but it's also responsible for where the matter is. Because you remember that those quantum fluctuations that got blown up really big by inflation actually seeded the growth of structure, the patterns of galaxies and clusters of galaxies in the universe. So quantum mechanics explains the universe. Thank you.
I'm just going to stand right here so that these microphones can pick me up because isn't working. So we have a few minutes to take a few questions, but just before we do, I have one thing to check with you, Nicole. Now, you said that the matter-antimatter asymmetry is created on the walls of these bubbles, and then the universe can tunnel between from the false to the true vacuum. And then you told us that we, at the moment, in our current universe, could tunnel at any moment from where we might be now in a so-called false vacuum in some metastable state into the true vacuum, and that everything as we know it will be destroyed. Is that true? I just need to check.
That is true, but the probability of that happening is very, very small. And if it does happen, it's not our problem, right?
It's a pretty good motivation to measure the properties of the Higgs in my book. So we'll have a few minutes to take some questions. So please raise your hand. I will have to ask you to shout out the question because I believe they haven't given us any handheld microphones, have they? So if you could be so kind when we call on you as to shout the question out loudly, and Professor Bell will repeat the question for the recording and then attempt to answer it for you. So I'm going to start up in the middle there. Yes, the one waiting. Yes.
I think I memorised it. I think it was slide 22. You had this diagram of the big M cycle. And what amazed me was the lower left-hand corner. I don't know whether this is artistic license, but you have the size of the universe is going down to below 10 to the minus 60 metres. 10 to the minus 60. The Planck length is 10 to the minus 35 metres.
Yeah, that doesn't sound right.
That's artistic. BS, be honest, or was it actually a series?
Do I need to go back to 22? Can we get there faster?
So I'll repeat the question. Was it on slide 22? There was a diagram of the size of the universe. Go down
to the left-hand corner. We have this select scale, radius, 10 to the minus 60 north, so I'm not sure whether it's below 60, but maybe a little bit above. Let's say 10 to the minus 56 or something. Now that's many orders of magnitude below the Planck length.
Yeah, below the Planck length, all bets are off, and we know our physical theories are not reliable at all. Yeah.
Right.
Great. That one's clear up. Artistic license at the bottom end of the plot there. So in the middle here, yeah? Yes, yeah.
I want to come back to this concept of tunnel. When Good proposed the hyperinflation model, he used the concept of an instanton in the bubble that you mentioned, which was powered by some kind of quantum fluctuations, and that's what gave the impetus to the expansion of the bubble such. And yet today you talked about sphalerons rather than instantons.
So I think you're talking about.
Sort of rephrase the question for the recording. Sorry.
So I think the question was about some proposal by Guth, who was one of the founders of cosmic inflation, talking about instanton models in which there were little baby universes where it was the beginning of inflation. And I talked about something called a spherulon. At that point, I wasn't talking about inflation. I was talking about the inflation's long gone by the time those spherulons are important.
So, different time scale, I guess. Yep. Great. The first person with their hand up was actually the person right up the back. If you could shout out your question, we'll try and hear it.
How equivalent is matter and antimatter insofar as if somehow there had been more antimatter than matter, would we still have galaxies? Or, given what you've described today, is a greater amount of matter being most likely outcome?
If the universe had been all antimatter and no matter, I mean, it's like a naming convention. I think we would have called it matter, right? Matter and antimatter are identical, save for swapping the conserved charges like electric charge. There's nothing to in our theories whether you produce more matter versus antimatter depends upon some parameters that are not fixed, that they could go either way. But if it had been all antimatter, I think we would have called it matter, right? It would have been the same.
From the experimental view as well, right? I guess the one thing that might be like, do they act differently under gravity? And then I know there's one experiment at CERN trying to measure that, whether there's a difference in how matter and antimatter respond to gravity. And so far, I think the answer.
So I think the answer, we would expect them to interact the same under gravity. Gravity couples to mass, and they have mass, and it's not anti-gravity because it's antimatter.
Great. I really apologise, but I think we're out of time for the evening because people have to get on with the rest of their evenings. But I would like to congratulate Nicole on coming up with 3 new potential band names, if you're looking for one. The first one that I identified, which is a word I've never heard before, is spelleron. Excellent band name. False vacuum, also an excellent one. And barrier number violation. So you can thank me later, please. Give me 1 second to just grab some flowers for Nicole, but while I'm doing that, please give Professor Nicole Bell a huge round of applause.
I put hand up that, yeah. Can you introduce me some book for about quantum physics?
Oh, that was me. That's you.
Lectures in physics. Next week, one of the professors
Appreciated that, thank you.
About quantum computing, and I have a good authority who's going to program a quantum computer live in this theatre next Friday evening. So please come along and see that. Thank you all again.